Here we have a graph of the function y of x. We want to rotate this piece of it from x equals a to x equals b around the x-axis. Now instead of getting the volume generated, we want the area of the surface that's generated. So what we do is consider 2 points that are close together on the curve, and consider what we get when we rotate this piece of the curve around the x-axis. We'll get this ribbon shown. The horizontal distance between these two close points is delta x, the vertical distance is delta y. So we assume that delta x and delta y are sufficiently small enough so that the hypotenuse of this right angled triangle, that is the straight line distance between these 2 points, is a very good approximation to the distance along the curve between these 2 points. So this red line is the straight line distance between these 2 points, the hypotenuse of this right angled triangle. So again, as we saw before, we apply Pythagoras' theorem. The length of the hypotenuse is the square root of delta x squared plus delta y squared. Now let's imagine we take this ribbon and cut it, say, straight across like that, and open it out. Well, the shape we will get will be approximately a rectangle, if we can imagine opening it out. It's going to be quite long, but I'm going to just try and fit it in here. This side of the rectangle is meant to be the straight line distance between this point and this point. In other words, root delta x squared plus delta y squared. So to a good approximation, that's what that is. We have a rectangle. Okay, so what's the distance all around? Well, that's the circumference of a circle whose radius is the distance from here to here. Okay, you might say it's the distance from here to here, but if these 2 points are sufficiently close, then these 2 circles are the same. They have the same radius. And the approximation will become exact, of course, when we let delta x go to 0. So what's the radius of the circle? Well, that's just a y value. And what's the circumference of a circle of radius r? Well, that's 2 pi r. 2 pi times the radius, where r is y. So to get the area, we multiply the 2 sides together. If to a good approximation, we have a rectangle, so it's 2 pi y times root delta x squared plus delta y squared. Now, just like we saw in the last video, we can divide what's inside by delta x squared, and of course we must compensate by multiplying by delta x squared with the square root of all of this. So we get 1 here for this term, and this is just delta y over delta x all squared, and we have to multiply by the square root of delta x squared. Well, that's just delta x. So when we just factorize out here, we have a delta x outside the square root sign. Okay, so this is the area of this ribbon, but of course we need to sum all of these ribbons from x equals a to x equals b. And that'll give us an approximation for the area generated. The approximation gets better and better as delta x goes to 0, so if we want the exact area, we take the limit of this sum as delta x goes to 0. And as we've seen a few times before, this limit can be written as an integral. So we're integrating from x equals a to b, all of this quantity. We replace delta x with dx, and delta y will go to 0 also, so we replace delta y with dy. So as these 2 points get closer and closer together, the approximation of this ribbon to a rectangle gets better and better. Both delta x and delta y will go to 0. So anyway, we end up getting this formula. Let's take this example. We want to get the area of the surface generated when the part of the curve y equals x cubed between x equals 0 and x equals 4 is rotated around the x-axis. So we need to get dy dx for this curve. Well, that's easy. That's just 3x squared. So we'll be plugging 3x squared in here and squaring it. We also have to plug in for y. Well, y is x cubed. We have to integrate, in this case, from 0 to 4. So 3x squared squared is 9x to the power of 4. Now you can see that x cubed is a multiple of the derivative of 9x to the power of 4. If we differentiate x to the 4, we get a cubic term. So that suggests we let u equal everything inside the square root sign. So we can get this term down to a single term. While this expression has two terms in it, it'll become a single term. So here's our substitution. If we differentiate, we get 36x cubed. So what do we replace dx with? Well, if we interchange dx and 36x cubed, we get du divided by 36x cubed equals dx. So we have du over 36x cubed here. And that cancels the x cubed here. And 2 into 36 gives us 18. We have 18 in the denominator, and we still have this pi. So we take the pi over 18 outside. And we have a straightforward integral. We're integrating u to the power of a half. So we add a 1 onto a half to get 3 halves, and we divide by 3 halves. That's the same as multiplying by 2 over 3. The limits were changed here, so when x is 0, we see that u is 1, and when x is 4, if we plug 4 into this and work it out, we get 2305. Let's take another example. Let's take y equals the square root of x in the interval 1 to 2. So here's a rough sketch. We'll just take the positive square root of x and rotate the piece of the curve between 1 and 2 about the x-axis and get the area of the surface generated. So we need dy dx. So that's a half x to the power of a half minus 1, which is minus a half. Okay, so here's our integral. So for y, we plug in x to the power of a half. So we have to square this quantity here. Well, that's going to give us a quarter x to the power of, we multiply 2 by minus a half, which is minus 1. So x to the power minus a half squared is x to the power minus 1. Now there's not much point in letting u equal what's inside the square root sign like we saw in the previous example, because the derivative of this quantity here is not actually a multiple of x to the power of a half, so it's not going to cancel this out when we sub in for dx. What we could do is combine these terms, because x to the power of a half is just the same as root x. So now when we multiply these terms, we can just multiply x by what's inside this square root, and we just have a single square root terms. X by 1 is x. X by a quarter x to the minus 1 is a quarter x to the 0, which is a quarter. Now to simplify this down, we just make the substitution u equals x plus a quarter, because then we're getting the square root of u. So we just this expression will reduce to an expression with just one term in it, the square root of u, which we can handle. What about dx? Well, that's straightforward. Du dx equals 1, so we can see that du is equal to dx. So now we get the square root of u, which is u to the power of a half. Dx equals du. Get a straightforward integral. As for the limits, when x is 1, u is 1 and a quarter, or 5 quarters. When x is 2, u is 2 and a quarter, or 9 quarters. So add 1 to half to get 3 halves, divide by 3 halves, that's multiplying by 2/3, and apply our limits. I won't bother doing this. If you work it out, you should get 8.28. As a final exercise, I'll get the surface area of a cone. That excludes the circular end of the cone. So here we have a straight line going through the origin. We want h to be the height of the cone. This distance here will be the radius of the cone. When we rotate this segment here around the x-axis. The slant height of the cone is normally called L, and we can see that L, R and H are linked by Pythagoras' theorem. Now the equation of this line is y equals mx plus c in general, where c is the intercept, but the intercept is 0, so it's just y equals mx, where m is the slope. Well, the slope is just, for this case, r over h. So for our formula we need dy dx and we need y. Well, dy dx is just the slope of this curve, or it's just a straight line, which is just r over h. It's just a constant. So we've plugged in for y. y is rx over h, that's here. Plug in for dy dx, so we have to square r over h. So this is just a constant, so we can actually take that outside along with the 2 pi r over h. So we have a straightforward integral of x with respect to x. Well, that's a half x squared. So we plug in our upper limit, which is h, so we get a half h squared. And of course we get 0 for the lower one. So these 2's cancel out, and we cancel out one of the h's. Now we can take 1 over h squared out of what's inside the square root sign. So if we factorize 1 over h squared out, well, I'll just go through it carefully. So we'll have to have a h squared plus r squared here. If you multiply 1 over h squared into this, we'll get 1 plus r squared over h squared. But the square root of 1 over h squared is just 1 over h, and it cancels out with this. So we're left with pi r times root h squared plus r squared. But then we can apply Pythagoras and see that root h squared plus r squared is just equal to L. So we end up with the familiar formula for the surface area of a cone, which is pi times r times L. Pi times the radius times the slant height. So this is the curved surface area of the cone. We weren't ignoring the circle, of course, that appears when we generate a cone this way.